This is Lesson 22 in our Calculus 2 series, Parametric Curves. Let's start this lesson by considering a particle traveling in the xy plane, where at any time t greater than or equal to 0, the x-coordinate is x equals radical t, and the y-coordinate is y equals e to the t. Let's plot the movement of this particle. The first thing we're going to do is make a table of data. We're going to list some t values and then find their corresponding x and y values. So here, because t is representing time, we have t values that are greater than or equal to 0. And so we'll plot for t equals 0, 1, 2, 3, and 4 in this problem. Now x is equal to radical t, so the corresponding x values are 0, 1, radical 2, radical 3, and radical 4, which equals 2. Now for plotting purposes, it's good to have an idea of what kind of numbers radical 2 and radical 3 are. So we find decimal approximations to help us plot. So radical 2 is approximately 1.4 and radical 3 approximately 1.7. And for the corresponding y values, y is equal to e to the t, so t is equal to 0, y is equal to e to the 0, or 1. When t is equal to 1, y is equal to e to the first, or e. And again, here we take decimal approximations just to help us plot. So we have e squared, e to the third, and e to the fourth as our corresponding y values. So when t equals 0, the particle is at the point 0, 1. That's here. At t equals 1, the particle is at 1, e. And similarly for the other 3 points, we're here. Now let's sketch the path of the particle. So as t increases, we want to show the direction in which the particle is moving. So we want to put these arrows here to show the direction. And this is our parametric curve. We call t the parameter here. Now we might be interested in finding the equation of this curve in terms of x and y. So in that case, we'd want to be able to eliminate the parameter for this curve. To find the equation of the curve in x and y without the parameter t, we have two methods. The first method is to solve for t in one equation and sub in to the other equation. And that's what we're going to use here. We have x equals radical t, so let's solve this equation for t. If we square both sides, we get t is equal to x squared. Okay, if t is equal to x squared, let's sub the x squared in for t here. Y is equal to e to the t, well, that's e to the x squared. So y is equal to e to the x squared. And that is the equation of this curve in terms of x and y. Method 2, to eliminate the parameter and find the equation of the curve in x and y, is to use identities, and we're going to see an example of that in a couple minutes. I want to point out here that the parametrized curve offers more information than just the equation in x and y, because the parametrized curve tells us at what time the particle is at any given point. It doesn't just show the set of points covered by the particle, it shows us when the particle is at each point. And with that, it shows the direction in which the particle is moving. I also want to point out that if the parameter represents time, then time should be greater than or equal to 0, because you have a starting time, t equals 0, and then time would move forward from there. But otherwise, for parametrized curves, t can span the entire real line, or it could be any given interval. Now let's take a look at this example. Eliminate the parameter t and find the equation in x and y. Here we're given x equals t plus 2 and y is equal to sine t. And we're going to use method 1 again here. That is, solve one equation for t and sub in to the other equation. So we solve our first equation for t, x is equal to t plus 2. That tells us t is equal to x minus 2. And then we'll sub x minus 2 in for t in the y equation. So we have y equals sine of x minus 2. Let's take a look at another. Eliminate the parameter t and find the equation in x and y. We have x equals 2 sine t and y equals 3 cosine t. And then plot the curve. Well, to eliminate the parameter and find the equation in x and y, we could solve for t and then sub in, but in this case it's going to be easier to use an identity that we know. We know that sine squared t plus cosine squared t is equal to 1. So if we divide the first equation by 2 and the second equation by 3, we're going to have x over 2 is equal to sine t, and y over 3 is equal to cosine t. And so sine squared t then becomes x over 2 quantity squared. And cosine squared t then becomes y over 3 quantity squared. And we know that this is equal to 1. So we have x squared over 4 plus y squared over 9 is equal to 1, and that's an ellipse. Now to plot, we start by making a table of data. So when t is equal to 0, we have x equals 0, y equals 3. X equals 0, y equals 3, we're here for t equals 0. Then for t equals pi over 4, we have x equals radical 2, y equals 3 radical 2 over 2, so that's approximately 1.4 comma 2.1. For t equals pi over 2, we have 2 comma 0, 2 comma 0, and so on for the rest of these points. And notice that t equals 2 pi, we're back at 0, 3. We're back at 0, 3. So our curve looks like this. And notice again, we're showing the orientation of the curve. We're showing the direction as t increases. Let's take a look at a matching problem now. Match the parametric equations with the corresponding curve. Explain your work. Okay, let's take a look at the equations we have. We have x equals t squared minus 1, y equals t to the 4th. X equals t minus 1, y equals t to the 3rd. X equals t squared minus 1, y equals sine t. X equals t squared minus 1, y equals sine 2t. X equals cosine 3t, y equals sine 2t. And x equals 3 cosine t, y equals 2 sine t. Okay, now where do we start? The first thing I want you to look out for is periodicity. See if the functions that you have for x and y are periodic. For example, with number 3, I can see that x is not periodic and y is periodic. This y value is going to be bounded between 1 and negative 1 because its values are the range of the sine function. And here we have x equals t squared minus 1. Think of the range that we have here. If x is equal to t squared minus 1, that's a parabola shifted down 1 unit. This is telling us that x is going to be greater than or equal to negative 1. Now let's take a look at the graphs and see which might represent these parametric equations. We have x greater than or equal to negative 1 and y bounded between negative 1 and 1. So these are all of our graphs. And it looks like it could be B or D because we have x greater than or equal to negative 1 in both cases, and the y values bounded between negative 1 and 1. Now let's take a look at the other equations we have. And notice that the equations in number 4 are very similar. But what's the difference here? The difference is that the y equation here has sine of 2t. That tells us the y values are changing faster for this parametric curve. So let's take a look at the two graphs again and see which is which. Notice that the y values in graph B are changing much faster. They make a full oscillation from 1 back up to 1 in maybe about 15 units, whereas here we're only making half an oscillation. We're going from 1 to negative 1 in about 20 units in x. So the y values in B are oscillating much faster, and that is going to be graph number 4. And graph number 3 is then going to be D. Now let's go back to the other equations and take a look at which ones look periodic. Here, with numbers 5 and 6, we see that both x and y are periodic. But notice the important difference between the placement of the 3 and the 2 in these equations. With number 5, this is x equals cosine 3t. These x values are the range of the cosine function. So here, x is going to be between -1 and 1. But in number 6, this is 3 times those values. So here we're taking the range of the cosine function and multiplying it by 3. So here we have x between -3 and 3. Here y is between -2 and 2, yet here y is between -1 and 1. So we've got x and y periodic, but their bounds are different. So notice in A we have x and y bounded by 1 and -1. And in C we have x going from -3 to 3 and y going from -2 to 2. So this is graph number 6 and this is graph number 5. Keep in mind we saw an equation very similar to this earlier in the lesson, and that was also an ellipse. Now let's take a look at equations 1 and 2. X equals t squared minus 1, y equals t to the 4th, x equals t minus 1, and y equals t to the 3rd. Notice here that x is going to be greater than or equal to -1 here. Again, it's the same t squared minus 1 that we had here. And y is going to be greater than or equal to 0. Where here, x can be any real number, and y can also be any real number. So let's see if that helps us determine which of the remaining two graphs is which. Here we see that we have some negative y values, and so this is definitely number 2. And this one is number 1. Notice also here that this looks like the x cubed graph moved over 1 unit to the left. And notice if we solve here for t, we get t equals x plus 1. So this is y equals x plus 1 to the 3rd power. And so that is the last graph, graph F. Here we have x greater than or equal to -1, y greater than or equal to 0, and that does in fact match graph E. Another thing I'd like to mention that might be helpful for these kinds of problems is to choose particular t values and find the corresponding x and y values that go with them. For example, if we choose t equals 0 in curve number 1, we know that x is going to equal -1 and y is going to equal 0. So we could go down and look at our graphs and see which one of the graphs has that point on it. Now, generally, plugging t-values in is a helpful idea, but in this set of graphs, we notice that 5 of the graphs go through the point -1, 0. So it doesn't really help us all that much for t equals 0. So then we would want to try different t-values and keep going with that, which could be a little bit of work. I think it's much more useful to talk about the periodicity and the ranges as we did above. Let's take a look at another problem. Plot the parametric curve x equals 5 sine t, y equals t squared for t values going from -pi to pi. Now in the problem we had above, I used increments of pi over 4 for our plotting. You certainly don't always have to use increments of pi over 4. You just want to make sure that you are getting enough data to show the shape of the curve. What's happening to the graph of x equals 5 sine t over the interval -pi to pi? We know that it starts at 0 and ends at 0 over this interval, but it goes up to 1 and down to -1 as well. So we want to make sure that we get that information. We know that at t equals pi over 2, it's going to go up to 1. At t equals -pi over 2, it's going to go down to -1. And so these x values will go up to 5 and -5. And so we want to make sure that at least we're getting that information in our table of data. So at least use increments of pi over 2 to plot this. So please take a few minutes, pause the video, and work on this. So here I'm using increments of pi over 2. Our x computations are quite easy. We have 0, -5, 0, 5, and 0. But for y equals t squared, we're getting values like pi square and pi square over 4. So it's helpful to have an approximation. Pi squared is very close to 10. So for purposes of plotting, it's useful to approximate this as 10. And so we have the point 0 pi squared. That's approximately the point 0, 10. And -5 comma pi square over 4 is approximately -5 comma 2.5. So when we plot our points, we're here. We're starting at 0 pi squared. And then we're going to -5 comma pi square over 4, then 0, 0, then 5 pi square over 4, and then back to 0 pi square. And so our curve looks like this. And again, we want to make sure we show the orientation, that is the direction in which t is increasing. And with this, we'll conclude our lesson on parametric curves.